Chapter 20, there we go, is about magnetic, well, just let's say it's about magnetism. It's about magnetic fields and magnetic forces. We're going to start with just a general talk about magnetism. Magnetism has been around. It was discovered over 2,500 years ago. I won't ask you that, so don't write it down. In a city that was known as Magnesia. Hence the word magnetism. They found it in little iron samplings, naturally occurring little pieces of ore in this city. That city today is called Manisa, and it's in Turkey. We know that Chinese sailors were among some of the earliest people to use it. They used compasses for the purposes of navigation, and that's been going on probably over 1,000 years. If a magnet is free to move, it will always rotate in a north-south direction. And because it will rotate in a north-south direction, the two poles of a magnet were named north and south. Really, you might want to think of them as having a north, we don't say the word seeking, but originally they did, a north seeking pole and a south seeking pole. All magnets have two poles. In other words, magnets are dipoles. They have two poles. We know that with these magnetic dipoles, that just like with electric charge, opposite poles attract. And like poles repel. I hope that sometime when you were in elementary school or middle school, you had an opportunity to really play with some magnets. Certainly that's not something we can do online. If we take a magnet and we cut it in two or break it in two or somehow damage it, what we find is all we've done now is create two magnets. Even if you make it really small, what we see when we look at magnets is even on a microscopic level, there's these little clusters of atoms called magnetic domains that behave like little miniature magnets. Scientists have tried to isolate magnetic monopoles, in other words, to get just a north pole or just to get the south pole in isolation. But they have never been able to do that. So at this time, there are no known magnetic monopoles. We generally classify most magnets as either being permanent. Those are the ones that you played with in elementary school. They're usually a mixture of iron, aluminum, nickel, and cobalt. The primary magnetic material is iron. That is the most commonly found in nature magnetic material. They put in the aluminum and nickel and the cobalt because it helps harden. Iron is actually, pure iron is very soft, so it makes an alloy that actually is better at maintaining its magnetism. They usually call these alnico, as in aluminum, nickel, and cobalt. That's not the only thing permanent magnets are made out of. There's some rare earth metals that make some magnets that are very, very strong and yet really still very, very small. One of them is called neodymium, and the other is gadolinium. Again, you can get maybe a magnet the size of a button and it'll be much stronger than a typical bar magnet. Some magnets are what we call temporary. Some materials are made out of iron or things that can be magnetized, but they're not magnetized. If you place these materials in a magnetic field, they will become magnetized while they're in the magnetic field. For example, if you have a magnet and you pick up a string of paper clips, those paper clips all become temporarily magnetized. So, magnetic materials that are placed in a magnetic field can become these temporary magnets. But most of the magnets that we deal with in the whole universe, most of the magnets are actually electromagnets. When you have electromagnets, you basically have magnetic effects produced by moving charges. A long time ago, it was believed that electrostatic forces and magnetic forces were actually two completely separate things, but we don't talk about it that way anymore. Now we talk about electromagnetic forces because we know that magnetism is just another manifestation of electric charge. So electricity, static electricity, those are due to electric charges, but magnetic effects are also due to electric charges. In particular, it involves moving electric charges. Let's talk a little bit about the magnetic field of the Earth. We know that, here's the Earth, that if we have a compass and we're standing up here we're somewhere up here in the northern half, that our compass will point north. And if somebody on this side of the Earth is over here, their compass will point north. In fact, if you're down here, their compass kind of tends to point north, no matter where you are. That's why we decided that this was the North Pole. North Pole. Who lives at the North Pole? Santa. Well, think about this. If all of these magnets, their North Pole is attracted to our geographic North Pole, that means in terms of a magnetic field, the Earth really behaves as if there is a giant bar magnet in it, and that the giant bar magnet would look like this. Compasses are attracted to the North Pole because the North Pole is the geographic, as in geography, geographic North Pole is a magnetic South Pole. Now, it's not a magnetic South Pole because there's a big bar magnet. We actually think that the magnetic field of the Earth is due to electric currents that are running through the center, the core. The Earth's core is made out of molten metal, and that allows electric currents to flow through it. So we think it's these eddy currents inside the core that actually cause the Earth to have a magnetic field. So our South Pole would be down here. Santa does not live at the South Pole, but penguins do. Okay. Now, one fun fact about the Earth's magnetic field is that it has not always been the way it is now. In fact, the Earth's magnetic field has reversed itself many times in history. They've discovered that by looking at the magnetic fields in fossils and things. It appears like the magnetic field of the Earth has probably reversed itself roughly every 500,000 years or so. The Earth's magnetic poles, that South Pole, it actually moves around a bit. Magnetic poles will wander around maybe as much as 10 miles per year. Um, our current magnetic field is actually weakening and getting a little bit wobbly, so to speak. They think we may be getting close to a reversal. That's going to be a really interesting phenomena, but we won't be around to see it. They're thinking maybe in a few thousand years, the Earth's magnetic field is going to reverse again. It's not known that the reversal of the magnetic field has ever caused a species to go extinct. I feel like scientists will know how to handle it when that occurs. But it might throw some things off in terms of using magnetic fields for navigation. Sailors are not the only people that have done that. They think certain bacteria, certain animals, possibly even things like whales, have used the Earth's magnetic field for the purposes of navigation. All right, to move on, let's talk a little bit more about magnetic forces. Let's go back and review just a little bit. We know that electric fields if we talk about electric fields, a charge distribution, whether it's one charge or lots of charges, at rest, creates an electric field we usually breathe that E in the surrounding space. We're going to do A and B or 1 or 2. Let's do 1 and 2. This electric field exerts a force call that force F, that's equal to QE on any charge Q in the field. Q is positive. Let's just throw this in. F and E are in the same direction. Now, if Q happens to be negative, they're going to be in opposite directions. So positive charges feel force in the direction of electric fields. Negative charges feel forces in the opposite direction. Okay, let's relate that to magnetic fields. There's going to be some similarities and yet some really important differences. Okay, a permanent magnet a moving charge or a current, and all a current is a whole bunch of moving charges, create a magnetic field and the symbol for a magnetic field is a B. Notice it's a vector field. I put an arrow over in the surrounding space. So very similar to the fact that we have stationary charges creating these electric fields, we know that a moving charge, whether that's a single charge or an electric current, or a permanent magnet. A permanent magnet does contain moving charges. The moving charge in a permanent magnet is actually called electron spin, and we're not going to go greatly in depth into that on an atomic level. But even permanent magnets, their magnetism is due to moving electric charges. So they create a magnetic field in the surrounding space, just like an electric charge at rest creates an electric field. And two, this magnetic field exerts a force on any other magnet or moving charge in the field. Now, one of the things that's going to be really interesting is the direction of the force is not the same as the direction of the magnetic field. It's also not the same as the direction the charge is moving. That's the hardest part when we start talking about magnetic fields and magnetic forces. These are three-dimensional problems. They cannot be solved in 2 dimensions, so it makes it a little bit harder to visualize. So let's talk about magnetic field lines. Well, magnetic field lines are tangent to the magnetic field at every point. That's very, very similar to electric field lines. Electric field lines are tangent to the electric field. Magnetic field lines are tangent to the magnetic field at every point. Outside of a permanent magnet, the lines point away from north poles and toward south poles. Now that kind of reminds us of electric field lines that point away from positive charges and towards negative charges. There really is a difference though, because these magnetic field lines don't actually start and stop on north and south poles. They actually form closed loops. Well, look at that. Magnetic field lines form closed loops. This is in part because we have dipoles. We never have a north pole without a south pole. And of course, just like in an electric field, the magnetic field lines are closer where the field is stronger. Usually this is going to be near the poles. As you get farther away from the poles, the field will get weaker. So let's look at what magnetic field lines look like for some familiar sorts of magnets. And we'll start with a bar magnet. And a bar magnet looks just like this. Sometimes you see them drawn with the little kind of cut in half. North Pole, South Pole. I'm going to get a different color for magnetic field lines. I guess I'll draw them in green. Now, if we're on the sides, I'll tell you what, they tend to be kind of weak, but they do come out of the North Pole and they do go into the South Pole. Notice they also go back through. Inside the magnet, it looks like they go from south to north, but outside of the magnet, they go from north to south. They look something like this, out of the north, so out of the north and into the south. If we come over here on this side, we see the same thing. They come out of the north, they go into the south. Inside, they're going the opposite way. Now, actually with a bar magnet, you're going to get the most strength at the ends. If we picture right here, kind of dead in the middle, I don't know what just happened there. Okay, dead in the middle, out of the north, into the south. But really what we see is we get lots of these closed loops. Same thing, out of the north, whoops, out of the north, into the south, out of the north. And the lines tend to be much stronger right here on the ends. I'm not going to draw all the closed loops, but they make those, you can see, it's coming out of the north everywhere. They're going back into the South Pole, but when we're inside that magnet, they're actually going from south to north. Notice you don't see lines very close together on the sides, but these lines are real close together over here and over here. Okay, that's pretty much the classic look of the magnetic field lines for a bar magnet. Let's look at a C-shaped magnet. Similar to the horseshoe, but it's a little bit different. C-shaped magnet looks like this. The big letter C. Again, it's going to have a north pole and a south pole. What we'll see is the magnetic field will come out of the North Pole into the South Pole, and then it actually travels around through the magnet itself. Magnetic field lines really do prefer to travel through magnets when possible. And here's another one. Again, not a perfectly drawn C shape by any means, but what we see is we will develop this uniform magnetic field between the North and the South Pole there. Reminds us of the uniform magnetic field we used to see between a positively charged plate and a negatively charged plate. All right. Those were both examples that involved a permanent magnet, and we already said, truthfully, most magnets are not permanent magnets. Most of the time, magnets are made actually using a wire, a current carrying wire. So let's just look at a straight current carrying. So we have charge flowing through it. Wire. So here we go, long straight wire. And we've got current. When I say current, I mean positive charge. This is our conventional current flowing through it. like that. It's going in this end, it's coming out this end. What's the magnetic field look like? Might surprise you. The magnetic field is actually formed what we call closed loops. Little circles around it, and they're concentric. There'll still be a magnet. If we get farther away, there's still a magnetic field. It's just not as strong. So all up and down this wire, you will get these closed loops of magnetic field. Now we're going to learn that there are lots and lots of what we call right-hand rules for determining the direction. But for a current carrying wire, the way you do it is you take picture, I'm going to go ahead and show you this. We're going to be doing lots of right-hand rules, and they're going to be tricky. You take your thumb and you put your thumb in the direction of the current. And then you take your fingers and you grab the wire. Oh, my fingers kind of got shorter. You grab that wire. Your fingers are going to curl, here's the rest of your hand, in the direction of the loops. So notice here the loops are coming this way. The fingers are curling this way. That's one of many right-hand rules. Now, another way we can think about this wire is to say, look, here's this long straight wire. I'm going to draw it a little more horizontal. The electric field seems to be coming out of the page at these points. We use dots to represent out of the page and into the page at these points. Again, remember, our current in this case is going this way. Those circles would come out of the page here and then go back into the page to form those closed loops. Out of the page is a dot. Sometimes you see it with a circle around it. Out of page. Into the page looks like an X. Sometimes you see that with a circle around it. Think of an arrow. If it's coming out, you see the tip of the arrow like a dot. If it's going into the page, you see the tail feathers of the arrow like an X. Okay, so a straight piece of wire has a magnetic field, and the magnetic field lines actually make concentric circles, these closed loops that go around the wire. Now, in order to make magnets, one of the things that we typically do is we take that piece of wire and we bend it into a loop. Here we have current going in this way, and current will be coming out. So our current, if you want to picture it, looks like this. If you picture the right-hand rule, grabbing that wire with your right hand and putting your thumb in the direction, you can see that on the outside, your fingers are going to be going into the page as you grab it. But on the inside, they'll be coming out. So we get something that looks like this. Notice the magnetic field is actually going to be stronger on the inside because those dots are going to be closer together than those X's. There's our closed loops. All the way around. Okay, now that will make a magnetic field that tends to point out of that loop, because inside of that loop, the magnetic field lines are coming out. On the outside of the loop, they're going into the page. Now, a single loop will not usually make a very strong magnet. So what we do, instead of doing a single loop, is we say, well, what if we have a whole bunch of loops? If I have a whole bunch of loops, I can make something called a solenoid. A solenoid is just a word that means a coil of wire. And these coils can be a lot closer than I'm drawing them, but that's a little tricky. So here's our coil. It's called a solenoid. Now, depending on how you look at this picture, you may think it's going one way or you may think it's going the other. I'm going to send current, I'll tell you what, erase that. I'm going to send current going into the wire this way. If I do, when I look at the loops and the direction of the loops, it's going to make a magnetic field. Let's see. And again, it depends on how you interpret this picture, and that's really hard to draw. So if yours looks different than what I'm drawing, it may just be the way you're interpreting. But the result is you generate a magnetic field that basically looks like a bar magnet. There'd be your North Pole, this would be your South. They would go through. Again, it tends to want to stay through, but it will form those closed loops. This is how most electromagnets are made. If we look up here at the top, that magnetic field looks very, very much like this magnetic field. So how strong a magnetic field are we going to make? Well, it depends on how we make it. But let's look at the magnetic force. We'll just look at the force on a moving charge. So in this case, we're just talking about one moving charge. We'll come back later and we'll look at if we have whole current. The formula says that it is equal to the absolute value of the charge. Well, that makes sense. We would feel like the larger the charge is, the greater the magnetic field it would generate, times velocity, that's the speed of the charge, times B, that's the strength of the magnetic field, sine phi. This is our basic formula for force on a moving charge. Q, of course, is simply charge. We measure that in coulombs. This is the velocity or the speed. And of course, we measure that in meters per second. B is the strength of the magnetic field. We haven't talked about what we measure that in yet. We measure that in Tesla. The symbol's a capital T. And phi is the angle between the velocity vector v and the magnetic field v. Now, that last part carries some implications. We're going to get the largest forces, and this is always going to be an acute angle. We're going to measure it generally from 0 to 90 degrees. Would we measure any reason? Up to 180? Well, actually, no, we should go up to 180, not just 90, because we are in a plane. It's going to be the shortest distance. So 0 to 180 degrees. What does that mean? That means that if phi equals 90, what does that mean? That means that the velocity is perpendicular to the magnetic field. We're going to get sine 90 equals 1. that's going to be the maximum force. So we get a maximum magnetic force when the moving charge is moving perpendicular to the magnetic field, not when it's moving in the same direction. In fact, if we look at our formula, if it equals 0, which means they're in the same direction, or 180, which of course means that they're in opposite directions, either one of those, sine phi is going to equal 0. There is no magnetic force on a charge that's already moving in the direction of the magnetic field. Magnetic fields only exert forces on moving charges if those charges have a component of velocity that's perpendicular to the magnetic field. Like I say, they can't be in the same direction. It is a little bit of a mystery then to say, okay, so what direction is the force? And that is tricky. And we're going to learn a rule to help us with it. But the force is always perpendicular to the plane that contains V and B. What does that mean? Well, picture for you are, just think in terms of north, south, east, west. Okay? If you have a magnetic field that points north to south, and you have a particle that's moving east to west, the force on that particle will either be straight up, perpendicular to that north, south, east, west plane, or straight down. That's really kind of hard to wrap your head around because it's not intuitive at all. If you go to YouTube, you can probably find lots of videos that try to explain directions for right-hand rules. When we're in class, I will certainly also try to explain them to you, but let's go right now and let's talk about what's commonly called the first right-hand rule. And it's first simply because it's the first one in this particular textbook. And this one's going to tell us the direction of force on a positive charge. All you need to know is if your charge happens to be negative, it will go in the opposite direction. Okay, so you have to use your right hand or this rule doesn't work. I've seen kids first point your fingers, and again, the fingers on your right hand in the direction of V. So if I tell you that the particle is moving along the positive x-axis on a piece of paper, try to point your fingers in the direction of the positive x-axis. Take your right hand, lay it down if you need to. Then curl your fingers, your fingers curl. You're going to end up making a fist. Toward B. Now, sometimes that's going to seem real natural, and sometimes you may need to rotate your hand. So a lot of times they'll say, go ahead and draw the two vectors. So let's suppose that we have B. In this picture, I'm going to let B point straight up. That would be like the positive y-axis. There's B. And here's V. If I take my right hand and I try to point my fingers in the direction of V, if my thumb is pointing up out of the paper, I can't curl towards V. So I have to flip my hand over. When I flip my hand over and I curl my fingers towards B, what I find is my thumb points into the page. My thumb points in the direction of force on a positive charge. Whoops. So I want to rotate my fingers this way. The only way I can take the fingers on my right hand and rotate them clockwise is if my thumb points into the board. That means into the board. So the force on positive is into the board. It takes a lot of practice. If we try again, this time let's suppose that's B and that's V. If I were to rotate the fingers on my right hand from V to B, my thumb would end up poking out. That means the force on a positive charge is out of the page or out of this screen. All right, let's try a different one. Suppose I tell you that V points directly into the paper. So my right hand, I point my fingers directly into my page. And B happens to point straight up. Well, in order to have my fingers point directly into the page, I'm going to have to rotate my hand so that my thumb points to the right. I'm going to see that if that's the case, the force on a positive charge would have to be to the right. It's very tricky. That force is always going to be in the plane that's perpendicular to the other two. So in this case, it's like B is on the positive y. The velocity looks to be in the direction of the positive z. And that produces a force. Wait, I said that wrong a minute ago. If V is into the board, that's an X. Let's draw that right. V is into the board, then yes, I've done it correctly. V into the board, rotate my fingers up to B, the force. So in this case, it looks like V looks like it's the negative Z axis. B looks like it's on the positive Y axis. And F is the positive X axis. Okay? Fingers point in the direction of V, but they have to be able to rotate or curl in the direction of B, and your thumb will point in the direction of force on a positive charge. It takes practice. All right, we use the term Tesla, but I didn't actually tell you what a Tesla is. One Tesla, and again, the symbol for a Tesla is a capital T, is equal to 1 Newton of force per am, so we're divided by, times meters. It's kind of awkward, but that's what it is. The Earth's magnetic field is approximately 5 times 10 to the negative 5 Tesla. Occasionally they ask you to use that. You can find it somewhere in the textbook, but just in case, there it is. So let's consider a couple of problems. Let's start with a fairly easy one to determine the correct path. Suppose we have a magnetic field into the paper or the page. That means we're going to see tail feathers, which looks like X's. There's my magnetic field. And I have a negative charge that initially has a velocity to the right. The question is, what will be the direction or the path? Will the path continue in a straight line? Will the path curve upwards? We'll call that path A. We'll call continuing in a straight line path B, or curving downward path C. If we use our right-hand rule, don't worry about the fact that it's negative yet. If I take my right hand, let me draw my right hand, and I point my fingers, here's my fingers, this way. In order to be able to curl them into the page, I'm going to need my hand this way. That means I'll be able to actually make a little fist when I curl my fingers, and my thumb will end up sticking straight up, right? What's that tell you? Well, my thumb tells me the direction of force and a positive charge. So a positive charge feels a force up. A positive charge would follow path A. But this isn't a positive charge. This is a negative charge. A negative charge will feel a force down. Well, if it feels a downward force, then it will follow path C. So the correct answer here is C. But you act initially as, don't worry about the charge, just what direction is it going? My fingers are pointing to the right, but they need to curl into the page. And the only way to take my right hand and curve it into the page is if my thumb is pointing up. So I know that my thumb will point up. That means the force on a positive charge will be up. And of course, a negative charge will do exactly the opposite. Let's do one more example, and then we'll probably take a break. Suppose that I have a magnetic field. It is 2.0 Tesla, and it points along the positive Z axis. I have a proton. We know for a proton that it has a charge of positive 1.6 times 10 to the negative 19 coulombs. And this particular proton has a speed that is 3 times 10 to the 5th meters per second. It's in the XZ plane. And it goes on to tell us that V makes a 30-degree angle to the Z-axis. So we'll try and draw this. There's the Y-axis. There's the X-axis. Here's the positive Z-axis. Now, our magnetic field I like to draw in green. So our magnetic field is pointing along the positive Z-axis. There it is. There's V. It's 2 Tesla. The velocity I'm going to draw in blue, and it's in this XZ plane, and it's making an angle of 30 degrees to the positive Z-axis, so there's V. If I put my fingers in the direction of V and I want to rotate them towards B, it seems pretty obvious that my thumb will have to point down. The only way I can take my right hand and rotate from V to B. So I can see if I use my right hand rule that my direction, and what color should I do F in? I'll do F in this purple color. It looks like F is going to point straight down when I get finished. So the direction of the force and again, it's a positive charge, so I just use the right-hand rule. I don't have to worry about going in the opposite direction. Is in the negative Y direction. Now to get the magnitude, I do that absolute value of Q, V, B, sine phi. So 1.6 times 10 to the negative 19, 3.0 times 10 to the 5th, 2.0 Tesla, sine of 30 degrees. And that gives me 4.8 times 10 to the negative 14th newtons in the negative Y direction. All right. So we're going to do one more thing so that we can completely finish up sections 20.1 and 20.2. And that's introduced a really interesting thing called a velocity selector. And a velocity selector does exactly what you think it would do. It selects the velocity for a beam of charged particles that pass through it. So let's picture first, let's make an electric field. If this is negative and this plate is positive, let's assume that we are going to send a beam of positive charges shooting in with some given velocity. Here they go. And our goal is for them to enter and leave in a straight line without being deflected. So they'll probably have this kind of blocked off where it's like a little narrow opening. And we want to see if the particles that enter can go right out through that opening at the other side. Now you notice if we have an electric field, in this case, the electric field, we have a uniform electric field that points to the left. That means that there's an electric force equal to QE that points to the left. On a positive charge. And we know we're going to assume we have a positive charge right now. Okay. Now what I'm going to do is I'm going to put a magnetic field that points straight into the page. Now if the magnetic field points straight into the page, let's use our right hand rule. My fingers on my right hand need to point straight down, and then I need to curl them into the page. The only way I can point them straight down and curl them into the page is if my thumb points to the right. So we're going to get a magnetic force. So now let's assume we have a uniform magnetic field into the page. And the result is that a magnetic field which equals QVB. Now sine phi is going to be 1 because they're at 90-degree angles to the right on this same positive charge. Our goal is the particle should go straight through. Well, the only way it's going to go straight through is if the force pulling it to the left is equal to the force pulling it to the right. So if the electric force is exactly equal to the magnetic force, if QE equals QVB, what we see is the charge is the same because they're the same particle, that the velocity is simply going to be equal to the ratio of E to B. Okay, that's how you select the velocity that goes through the velocity. Now, interestingly enough, if the charge is negative, the electric force is to the right, and the magnetic force will also be reversed. It will be to the left. So it reverses both forces. We don't actually have to do anything to our velocity selector. We don't have to make any changes. It will still work perfectly. Let's try an example. This is kind of tricky. Which plate needs to be positive if we want to make a velocity selector? So here's one plate. Here's another plate. They show that we have a magnetic field that's pointing out, straight out at us. So there it is, it's pointing out, it's nice and uniform For our purposes, let's just assume we have a positive charge that's going to enter right at the middle, and we want it to be able to keep straight on going like this. So you can think of this kind of being blocked off. We want that charge to follow a straight path. Well, if we look at the magnetic force, we need to figure out its direction. If the particles are moving with a velocity to the right, then I need to put my right hand, my fingers to the right, and they need to be able to curl out of the board. That force is coming out. So I have to kind of flip my hand over in an awkward thing, and I realize that my thumb points down. The magnetic force is down. What's that mean? That means that I need the electric force must be up. Well, if I want the electric force to be up, then I need to make sure this bottom plate is positive. If the bottom plate is positive, then the electric force will point straight up. Let's see if I can find a problem real quick, as long as I'm still going. Let's look in the back. Let's look at problem 10. Problem 10 is pretty tricky. You know what? Let's not look at problem 10. Let's save that for class, and let's just stop this video right here for now.